This is a production of Cornell University.
All right. So, gravitational potential. That's that positive potential pulling something down through gravity. How does it work? Here's our relative energy point. This is our reference point. Potential energy of 0. That would be that 0 graph. And basically what you're looking at here is the positive side of that graph. Okay? The higher that waterfall is, the higher that potential energy, the more positive it is. Does that make sense? Okay. The energy of the water that is potentially available to be released when it goes over that waterfall. Okay? Water flowing downhill under gravity. The reference point is the base of that profile. That's the 0. It's the bottom. You can sort of imagine this is the bottom of the rooting zone. Okay? Psi g, gravitational potential, is always a positive value. Okay? Now, let's go back and look at all these potentials. The first potential is psi g. Gravitational potential, it's a positive value. It's determined by the height of the water over that reference point, whatever that reference point is. For us, often it's that thought where the rooting depth is. Okay? It could be the bottom of your drainage ditch. Okay? It could be wherever whatever you're looking at. That's the potential break. Okay? Water flows downhill. The next one is matrix potential. This is a negative value. This is the suction. This is the pressure being pulled up, okay, against gravity. Determines the strength of the attraction of the material, whatever it happens to be, to that water. It's the soil matrix, imagine. Okay, that sponge, you can certainly imagine if I had a coarse sponge with big holes in it versus a finer sponge with smaller holes in it, that sponge would hold more or less water. Okay, I've got a sponge with big holes versus a sponge with small holes. Which sponge is going to hold more water against gravity? Small, because it's got more capillary action. It's got more surface areas for that water to be attracted to, and that water attraction then holding all the other water. Okay? It's the most important flow when we're talking about unsaturated flow, when the system is drier. It doesn't have saturated, it's not saturated like that sponge is at this point. Imagine what it was like when I started wetting that sponge. Okay? Water flows from zones of wet to zones of dry. Zones of less negative to zones of more negative potential. Okay? What we saw there was basically the interaction of these two. Now, there are two other potentials that you should be aware of. The first one is the solute, or osmotic potential. And this is created by salt gradients. It works very similar to the matrix potential. Okay? Yet, it works within the water. Imagine I have, maybe draw this one. This might be better to draw. So imagine I have a double tube of water. Okay? The water level's right here. It's equal. Does that make sense? Has anybody used like a hose balance or something like that, or a hose level where you take the hoses and you play with the water, and you can, if you lift this one up, you shoot water out the other side? That's sort of an arrow. Okay? This kind we're going to keep them balanced. Okay? And into this, we put a semi-penetrable membrane. Okay? There's some sort of barrier right here. Okay? This barrier it's microscale, and the only thing that actually can pass through it is water. Does that make sense? Okay. Now what's going to happen if I add salt to this side? So this is an osmotic barrier. Okay? If I put salt on this side, I'm going to increase that concentration. Salt, not sulfur. It's going to come up on this side. There's no salt on that side. What's going to happen? The water is going to migrate this way, right? Because salts can't migrate that way because of this barrier. And if that's the case, the water level is going to go up here, and it's going to go down here. Now for salt systems, for soil systems, this is not a big deal because there isn't really any permeable membranes in the soil system. But how about plants? Has anybody ever, you got to go back to that pot of yours, right? And after a couple years of watering it, you start building up salt concentrations on the edges and stuff like that? Okay, has anybody seen that? You know, you get that white salt stuff that starts to build up. What is that doing to your plants? It's making it harder for for the plants to suck in water. In essence, if it gets too high, it's going to pull water out of your plants. All right, so imagine this is my plant, right? And plants have semi-permeable membranes, osmotic membranes. And my soil water out here gets salty. What's going to happen to my plant? The water is going to be derived out of the system, out of my plant, and my plant's going to go into drought stress. Salinization of soils. This is exactly what happens. When soils get salty for salinization, plants start dying because not that there isn't water in the system, but they can't suck that water against this osmotic gradient. Okay? Now, the truth is they need some of these salts. These salts potentially are fertilizer. These are nutrients. But if you put too much nutrients in your system, your plants are going to start dying. That's osmotic pressure. That's the osmotic potential. The higher this salt content goes, the more negative that value becomes. The more negative that value becomes, the more water is going to move towards that value, or towards that salt. Does that make sense? Okay. The last one that you should know about is the pressure potential. This one can be positive or negative. Has anybody heard of artesian effects? Artesian waters? Okay, basically it's a pressure gradient. Okay, if I have water, okay, and I pressurize this end of it, okay, I have water and I pressurize it, what's going to happen? It's going to flow out of the system, right? Okay, imagine that I have this pressurized system, very simple pressurized system. We have a lot of these around here. Here's a hill slope. Okay, and someplace in this hill slope I have a hard barrier, a fragipan. It rains up here. Okay, water gets in here, gets underneath this. Water moves underground, right? Okay? That water, by the time it gets down here, because it can't escape through this line, because it's a barrier, by the time it gets down here, it has a pressure head of this much. And if I keep putting water at this end, there's going to be a lot of pressure on the water down at this end. Make sense? I now have a fountain coming out here. This week, you guys are going to be going to Caldwell Field. Caldwell Field is lake-laid material. Okay? It rains out there. It gets really wet. Okay? And so what they do, because it's an agricultural field, they put tile drains in. Basically, these are basically drains at the bottom of the soil. Okay? In the soil, basically just below the rooting depth. Okay? Let's go back to this drawing right here. The slope at Caldwell Field is not quite this dramatic, okay? But what they have is they have drains in here, just below the rooting depth, okay? And the drain, it starts raining here. The idea is for the water to get in here, and then it will escape. They have an escape channel on it, and it comes right out and goes into something, some sort of collection basin, okay? Make sense? What's going to happen to this drain, though, if I have something, you have a blowout here? The drain collapses. All the water that is now in this tube, the tile drain, is now pressurized because, well, it's pushing the height of the water from here to here is pushing the water here. If this water doesn't have an escape route, it's going to get built, the pressure is going to build, right? Okay, and if I have a break here, what do you think is going to happen? It's going to shoot right out. Caldwell Field, a couple years ago, we had a water fountain. Actually, it was rather dramatic. It was maybe 6 feet high of this just shooting out because we had a collapse in a drain. Something might have crawled in and died, or A tractor went over something and crushed part of the drain. Okay? This is an artesian effect. It's a pressure event. Okay? At a much smaller scale, this is pretty dramatic. At a much smaller scale, though, imagine what happens at the interface of the soil surface with the air when I have a new weather event come in. A change in pressure, a low pressure to a high pressure, or a high pressure to a low pressure, as it moves in. Now, this is very small scale. It's nothing quite as dramatic as the water fountain over there. But what's going to happen when I have a weather front coming in that brings in a new pressure system? I've got one pressure in my soil, higher pressure or low pressure here. It's going to take a while for it to equilibrate with the soil. That means it's going to pressurize and move things. Does that make sense? How about this? What happens if I have a fairly dry soil? And you guys will see this when we get up to the golf course. What happens if I have a fairly dry soil, and it's a fairly tightly poured soil, so it's a fine pipes, okay, and I have a torrential rain event? And all of a sudden I have ponding. The pressure of the water actually will prevent it from getting into the soil. Imagine this. I have a pore. Okay, here's my soil surface. I have a pore. This pore is dry, lots of air in there. And suddenly I have a rain event that puts standing water on top. That water wants to go down that pipe, right? But for that water to go down the pipe, the air actually has to be able to escape, right? And what will happen is I'll get a bubble stopped right there, and it will prevent the water from getting down. If you don't believe me, go buy a bottle of soda. Take the cap off the soda, turn it upside down. What happens? Glug, 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 glug. Does that sound familiar? That's the water and air exchanging. The water can't get in, or the water can't come out of the bottle until the air gets in. Now, that's a pressure. You've created a vacuum up there, and that's part of the problem. But for you to be able to get that water to pour out, you have to turn the bottle on the side so there's an air channel and a water channel so they can exchange at an equal rate. The same thing's happening here. It's a pressure change. I've pressurized this system. The oxygen can't get out of the system, and so as a result, I perch. Now, given time, this water will find a way out, and you'll start getting water going. This air will have a way to get out, and ultimately the water will get down. Okay? But you certainly imagine at a small scale, this can be pretty dramatic. Okay? Good example of pressure potentials. Okay. We feel comfortable with this so far? We feel comfortable with the 4 different potentials? Okay. When you put all those potentials together, you basically get the total potential. Now, with soil systems, the things that we mostly work with are, because those are the ones that are most prevalent, is the gravitational and the matrix potential. Solute potential comes into play big time when we start talking about plants. Pressure potential is a stochastic event or a very rare event based on landscape positions and things like that. Okay, we feel comfortable with this so far? Yeah? Okay, so does this graph make a little bit more sense? This is the reference point. When we talk about the reference, this is an arbitrary point, a point that you determine, wherever it happens to be. The bottom of my field, the top of my field, the middle of my glass of water. Okay? Above it, gravitational pull on that water, positive value, pulling it down. Against that gravitational pull, I have the matrix potential, that adhesion, cohesion, that the surface areas of those soils holding that water against gravity. The more negative that potential, the more water it will hold against gravity. The higher the positive potential, the farther that water is falling, i.e. when I took the sponge and it was this way versus when I put the sponge this way. When I moved the sponge from this to this, that potential got bigger. So there was more pull, and so more water came out. Make sense? Okay.
This has been a production of Cornell University, on the web at cornell.edu.